In a previous chapter, when we talked about derivatives, we started our discussion with the idea of derivative, and then we took the derivative of a number of polynomial functions and some of its close cousins. But then we needed new techniques to deal with situations like composite functions, and we introduced the chain rule to deal with that. Now, with integration, it's a similar kind of thing. We can integrate functions that are polynomial functions, and again, some of its close cousins, but it's a different matter to deal with something like composite functions. Now, the chain rule can help us understand what is going on, and we're going to look at two distinct kind of techniques here. With the simpler composite function structure, we can just look at pattern recognition, and that's what we're going to do at first. Remember that the chain rule now is this, that the derivative of f of g of x, a composite function structure, is f prime in terms of g of x times the derivative of the g function. And another way to look at it using the u notation is like this. If we have y is f of an expression u, plus some constant c, and I'm throwing the constant in here because we're going to work this backwards, but usually we wouldn't even see the c part of this when we were using the chain rule. I'm just emphasizing that if a constant is in here, it could be, and it would be fine, and here's what we would get for the derivative. The constant would go out, you see. So the derivative of y prime, is f prime in terms of u times the u prime. And this is perhaps the simplest way to look at the application of the chain rule. Now with integration, we're going to work this in reverse, and all we need to do is recognize the pattern that we have here in order to move to this kind of structure. Now when we have this notation of the prime when we talk about derivative, and we have a different notation when we go in the other direction. When we talk integral, we talk about the integral function as a function designated with an uppercase f. So if we think in terms of this derivative function, this f prime of u, as just being a function of u, then the integral function, this function that we would have started with, would have been big F of u. So we can think of this then in terms of integration. If we integrate this, then we get that. I think an example goes a long way to tell us how this situation is working. Here's an example of a specific problem, and we're going to take it from the very top. That is, we're going to differentiate first. We're going to use the chain rule, and then we're going to use the chain rule sort of in reverse in order to integrate. So it looks like this. So we have y is 1/5 x squared plus 1 to the 5th plus 3. Now if we were differentiating this, if we want the derivative of this, then we would recognize the situation as an inner function, an outer function, you see, and with that kind of structure we implement the chain rule. And the chain rule says to take the derivative of this, now this just goes out, it's just clutter, so the constant will go out, but take the derivative of this in terms of this single entity. So the 5 times 1/5 raised to a power 1 less than that, and then you multiply that times the derivative of the single entity. So we have 1/5 times 5 times single entity to the 4th times the derivative of this is 2x. And now it's a matter of cleaning up. The 1/5 times 5 is 1, and we just bring these things down. Now, now we're going to go in the other direction. We're going to say, well, let's say we have this and we want to move up here. And it's just a matter of recognizing that we have an inner function, an outer function, and we have the derivative of the inner function. That's an important property in this recognition process. So it's inner function, outer function, and derivative of the inner function. And once we have that, we can take the integral of that rascal, and it turns out to be the integral function of this outer structure plus a constant, and that's it. So it's x squared plus 1 raised to 1 power greater than this over that same exponent. And then 1/5, this can be expressed as 1/5 x squared plus 1 to the 5th plus c. Now, notice the plus c here is tacked on. Look at this and look way up here at what we started with, it's the same thing. We had a specific constant here, and when we integrate back, we're getting a general constant. That's the only difference in these two expressions. Well, here's another way to look at it. It's the same idea, just another notation or a variation on the same notation. We have the inner function g of x. The outer function is this raising to the fourth power, and we have the derivative of the inner function. And when we have that structure, we can take the integral of that structure, and the way we integrate is to take the antiderivative of this, and we get that. Okay, antidifferentiation then of a composite function. And again, here's the same structure once again right here. We're integrating f of g of x times g prime of x. Here's the structure we're recognizing. When we recognize it, it's the integral function of the g of x, and then plus a constant. Now, before I go into the next part on the board, I mentioned to you that there are a couple of techniques that we're going to look at. One of them is pattern recognition, and that's pretty neat as long as we can, we want to be able to recognize the pattern, but sometimes the pattern doesn't exactly fit, and so we have to use some varying techniques. And the techniques will be the substitution of a variable, and that variable substitution will involve the u. And to get us ready for that, I want to show you this in terms of the substitution idea, or in terms of the u notation, just so that we can get familiar with that notation. You see, the u can stand in for g of x. And this part, the g prime of x dx, can be du, you see. So it's f of u du, so we're integrating this. The du now is the g prime of x dx, and we get, once we have this, then the antiderivative is the antiderivative function of the u plus a constant. All right, the pattern, the situation can go very, very rapidly once we see the pattern, and we can see it very, very quickly. Here, for example, in integrating this, where we look at the structure like this. We have this inner function. It's raised to the third power. We don't care what that exponent is. It's this inner function that we're really concentrating on, and whether or not that part is the derivative of this part, you see, and it is. So, and the derivative here would be negative 4x, so we do indeed have the pattern that we're looking for. So to integrate, we're integrating this, you see, in terms of that single entity. So it's this single entity raised to 1 power greater over that same exponent, and then plus a constant, and clean it up a little bit, and it looks like this. Now, a lot of times we can check these rather easily by performing the inverse operation. That is just by differentiating. So if we want to check this situation, we're starting out with y equals this, and then y prime then is, well, let's see, using the chain rule, it would be 4 times 1/4 times the single entity to an exponent 1 less than that, times the derivative of the interior, which is the negative 4x. Cleaning it up, then we have y prime is this, and this is exactly what we started with. So we have verified that the integration was done correctly. We can even establish a general power rule for integration. And that general power rule looks like this. This is just a variation on the same theme we've been talking about all along. We have used this general power rule in specific cases so many times that this is rather obvious, but it's this g function, this sort of inner function raised to some exponent, and here's the derivative of that inner function. This is the pattern we're looking for. And when we integrate, we get the antiderivative function of gx, so it's gx to the n plus 1 over n plus 1 plus c. And alternatively, with using the u notation, it's the integral of u to the n du is u to the n plus 1 over n plus 1 plus c. Okay. And using it, we can usually use it rather rapidly. I'm going to show you a couple more problems here, and we're going to march through them, and we're going to see through the substitution rather easily. I think if we have this situation, we notice that the 3 is the derivative of the 3x, and so we have the pattern that we need, and we could go right from this step to the answer if we want to. But let me massage it a little bit and make this so abundantly clear that, well, I should say redundantly clear perhaps, but just swap these two, and then it's in the form of the u to the 4th du, you see, and this is the form where we can use that general power rule. This is u to the 5th over 5 plus c, and we can do the back substitution here to put us back into the format with the binomial. And we could massage this even further, writing the 1/5 over here as an outside factor, but I think the point is rather clear. Now, it is possible here just to go from the original step down to here, if we can see through it rather easily, and feel free to do that if you want to. But I'm just emphasizing the idea of using that U notation in a problem like this. And sometimes, as we saw earlier, it's useful, very useful and needed to make that substitution. Other times it's really not important to use it at all. Here's another one. We have the integral of 3x squared times the square root of x cubed minus 2. Now, notice this part, our inner function is x cubed minus 2. And the exponent on x cubed minus 2 is 1/2. And I suggest that we burn a step to write that. Even if we're trying to do these rather quickly without using the u notation, it's, I think, important to write this as x cubed minus 2 to the 1/2 power. And now we bring this down. Notice I brought it down on the other side to kind of make it look like this g of x to some exponent times g prime of x form. But at any rate, we can go directly into the antiderivative idea here. Antiderivative of this is inner or single entity to 1 plus 1/2, that's 3/2 over 3/2 plus c. And again, we could clean it up a little bit, but this is the essence of it. Here's another one, and again here I want to show you a quick manipulation to get us into the form right quick to perform the integration. This binomial in the denominator, we want to just shift it to the numerator, so we would write this as 1 minus 2x squared to the negative 2 power, and then the negative 4x as the other factor. And then we just want to check to make sure that negative 4x is the derivative of this, and it is indeed, and therefore we're in the pattern that we want to, so we take the antiderivative function of this single entity to the negative 2 power. So it's the single entity to the negative 1 over negative 1, and again we could clean it up a little bit, and also the plus c is tacked on. Here's an interesting situation. It's x squared plus 1 squared dx. Now we would like to integrate here, and we might begin our thought process here by thinking, well, okay, let's make the substitution and see if we can follow our nose through it and see if some good things happen. We'll let u stand for the x squared plus 1. Now du then, the derivative of this would be 2x dx. Now, if we're going to try to solve this for dx, we would have du over 2x is dx. Gee, that doesn't help us very much. If we substitute this back into here, or when we write the next step, we still have an x involved in the problem, and we're trying to eliminate all of the factors of x or the references to x. So we'd have to take another tactic here, and that other tactic is quite simply to expand this expression. So we could write this then as x squared plus 1 squared. Let's square this. We get x to the 4th plus 2x squared plus 1, and then just bring down the dx. Wow, that's neat. Just by expanding, this becomes a rather easy integration problem. We're taking the integral of this and this and this all separately, you see, so it turns out to be, let's see, this is x to the 5th over 5 plus 2 times x cubed over 3 plus 1x, then plus a constant. and that's all there is to it. Again, we could clean it up a little bit, but I think we can see the cleanup rather easily. The point is, we didn't need to go through this sophisticated idea of substitution or using the general power rule or anything like that. All we do is expand what we see, and some very nice things happened.